Here we're asked to use differentials to approximate the square root of 8.6. And the first thing that I will note is that 8.6 isn't that far away from 9, and we know the square root of 9 is 3. So we expect this to be a little bit less than 3. And that's going to be information that we can use to help us with our process. So we know in general that if we wrote down a function here, we'd be considering the function f of x is equal to the square root of x. And we can further write that f of x plus delta x is approximately f of x plus f prime of x times dx. In this case, that's going to be approximately the square root of x plus 1 divided by 2 times the square root of x dx. Now if we go and take and kind of plug some numbers in here, that says that the square root of 8.6 is going to be about the square root of 9 plus 1 divided by 2 times the square root of 9 times a negative 0.4. That's the difference between 9 and the 8.6. That's kind of what our delta x is in this case. So we're going to end up with approximately 3 plus 1 over 6 times negative 0.4. And if we run that through our calculator, that's going to give us 3 minus 0.4 divided by 6, or about 2.9333. That's our approximation. If we actually just type it in and use the calculator to get an exact value, square root of 8.6, we get about 2.9326. So exactly 2.9326. Those two values are pretty close together, and if we round to just 3 decimal places, we would have exactly the same value. So the difference starts to happen in the 4th decimal place. Not a lot of work. Different kind of a method than what we saw with Newton's method, but still effective. More effective the closer we are to whatever x value we choose. More effective, that is, the smaller the delta x is. If we tried to use this, for instance, for the square root of 7, which was a number we looked at in terms of Newton's method, probably wouldn't work quite as well as Newton's method did, because our delta becomes so large in that case.